Hello. It's tradition in a revision seminar for me to show my face at least once. So for you in the room, I'm David. And you online, I'm David. And you know what I look like. So on the video, you won't see me again probably. But you guys have to look at me the whole time. So that's your issue. So hello. I'm David. I'm the coordinator of the Maths Learning Centre. This is a revision seminar for Maths for Data Science. It's Semester 2, 2019. It's also, this course has another name for the postgraduate students, but I can't remember what the name for the postgraduate students is. But the content is roughly the same. And this is the first semester that this course has ever been taught. So if you're watching this in 2020 or the future, hello from the very first time this course has ever been taught. We're all still figuring out what's going on in this course at the university because it's new. So what I've got is some requests of things to talk about, and the first things are about Taylor series and infinite series. And so I will talk about those things first, and then we'll see what happens after that. Okay, so I'm just going to talk. The rules is this is your revision seminar, so feel free to interrupt me if I make a mistake, especially if I make a mistake. If you say, David, shouldn't that be a minus? I say, yes, thank you. If I say something you're not sure what it means, please ask. And if I seem to have forgotten something that your lecturer mentioned, then ask. And if while I'm talking you think of something that you would like me to say, then ask. It's your revision seminar. So just make sure you have control over this. So I would like to start by just saying what I think a Taylor series is for, and it seems to match what's in your lecturer's official printed notes. Right, or also Taylor polynomial, that's another thing as well. Just let me check some terminology. Okay. So, the idea here is that mathematicians think that polynomials are nice. They're good functions because we know how they work. And so in a mathematician's mind, polynomials are the nicest functions. And the reason we think they're the nicest is for multiple reasons. You know, we know what they look like. It's easy to do calculus on them compared to other things. There's just one consistent rule, multiply by the current power, and put the power down by 1. And it's easy to teach a computer to calculate them because making a polynomial is essentially just a combination of adding and multiplying, and computers can do those things. It's easy to teach make a computer do calculations. And so they're really nice. And so not just to a mathematician, but to a computer scientist, polynomials are nice as well. And so it would be even better if all functions were polynomials. Just make sure that you know what I mean by a polynomial. That means something like 3 plus x. Or, for example, x squared minus 3x plus 7, or anything like that. a naught plus a1x plus all the way up to an x to the power of n. That's what a polynomial is, okay? And normally we see them with a function like that. And normally you write them with a p for polynomial. Okay, so they're really nice functions, and it would be good if all functions were like that, but they're not. There are some famous functions like sine and cosine and exponentials and logarithms that are very useful but are not polynomials. And so what we're going to attempt to do is to write those other functions as if they were polynomials. Lots of good functions are not polynomials. And so how are we going to get around that fact? So we're going to get around it in two ways. Well, if they're not polynomials, what we could do is we could find a polynomial that's pretty close, that usually gives, when you put x's in, the answers it spits out are very close to the original function. So we have two ways to deal with that. Approximate them. You may be able to see that I'm slightly dyslexic. So when I write a word, I don't always write the next letter first. I often choose a random letter and just write it down. So just bear with me with my spelling. It takes me a while to get the correct order. So approximate with polynomials. Or two, make the powers go on forever. So these are our two ways of dealing with the fact that lots of good functions are not polynomials. And this idea, number one, is what Taylor polynomials are for. And we have like the remainder. And this here is what Taylor series are for. Right. And so these two things, the Taylor polynomials and remainders, answers the question of approximating functions with polynomials, and the Taylor series answers the question of making the powers go on forever so that they're actually equal. Okay. So I'm going to talk about both of those things, but that's where I'm going with this. I'm just trying to get a handle on what these things do. Okay. So one. So our goal is to try and find a polynomial that is as close as possible to our function in terms of what it looks like on the graph. So I'm going to go over to my computer and go to here. This is Desmos, and it's a lovely little drawing program. Have you seen it before? Good. Did the lecturer use it? No. Okay. This is Desmos, and you could write any function you wanted. For example, that, and that's what it looks like. It's goes up very fast when x is big, but it's very close to the x-axis over here. And what we would like to do is attempt to find a polynomial that is very close to this. So, for example, I could do that one's not too bad. If I zoom right into this, when I'm very close, you can't tell the difference between these two graphs. And that's the idea I'm trying to get at. But unfortunately, this one is not so good if I'm not very close to the origin. So maybe I'd like to add another bit with an x squared. And that one's just a little bit better. And it may be that it would be better if I had some other coefficient. Oh, that's pretty good. And so what I would like to do is try and figure out what coefficients I should have for these powers of x in order to get it to be as close as possible to my function. That's what I would like. Okay. And it may be that I'm not actually interested in it being the right answer when x is 0. Maybe I'm interested in it being the right answer when x is, say, 1. Well, that's pretty high up. Or maybe a half. Let's go a half. And for that, I'd have to choose something else entirely, because this one is not very good when x is equal to a half. So maybe I might need to go that one's pretty good, that one's much better. A different slope would probably be better than that. Oh, poo. That one's pretty good. It's in a good spot. But I could guess for hours and never get a good one. And so the idea is that Taylor and Maclaurin, back in the day, in I don't know when it was, 1700s I think, figured out that the best choices for what those coefficients are based on the derivative of the original function. So you have a function f of x, and you approximate with a polynomial like this. Like that. And I'm going to say Pn because the biggest power is n. And the best choices for those coefficients involve the derivatives of f. That's the idea. And it may be that you would prefer to have it not based on how far you are from, not based on the actual value of x, but based on how far your x is from a particular other number. I think your lecturer called this number a. So you don't have to just have x's. You can have x minus something, and that's okay. What that will do is make sure that it works at the point where x is equal to a. And it turns out that the best choice for these numbers, a1, a2, etc., the best choices are a0 is f of this number a that I'm thinking of, and a1 is f dashed of this number a, and a2 is f the second derivative of this number of f with this number a subbed in, and a3, except this has to be divided by 2, and a3 is the third derivative of a divided by 3 times 2. And a4 is the fourth derivative. That's how we write the fourth derivative, in brackets with a number there. Because we can't just keep writing lots more and more dashes. It'll be ridiculous. And so on. So the nth one is the nth derivative with a subbed in divided by n factorial, which is what you get when you multiply n times n minus 1 times like this. Because even better, we can make this work. Look at this. This is the same as divided by 1. This is the same as having a times 1 there. And that makes the factorial work. That's what factorial means, this thing here. Okay? So that is the best choice that we could possibly have for those coefficients, for it to be as close as possible to my function. All right. I feel like this will make, we need to do a proper example of finding one. So let's do one. Oh, just a second before I write that. So if you do use these coefficients, then Pnx is called the nth Taylor polynomial for f of x at x equals a. And you should know that some people don't call it the nth Taylor polynomial, they call it the Taylor polynomial of degree n. That's the official name. And I should also point out that the letter A will not usually appear when someone asks you to make a Taylor polynomial. And so it's the grammar that tells you which one is the letter A. And some people also call this letter A the center. So it could also be, it could be around x equals a, or about x equals a, or with center x equals a. All of those are perfectly acceptable ways of saying it. Just so you know, because people don't always use exactly the same words. And as long as there is some phrase that indicates that this x equals a is a place, a location, then that's the number you should be using. Yeah. Cool. So I'm just, they also call it a Taylor polynomial of order n as well. So if you're searching for resources online, it's useful to know all these different terminologies. Okay. So let me do an example. Find the Taylor polynomial of degree 4 for f of x, which is going to be x e to the power of x, which is the one that I've put on my screen, at x equals 0. Actually, can I just change the problem, if that's okay? I'm going to go x minus 1 at x equals 1, just so that you can see what it looks like when it's not 0. And I'll go change my picture on the computer as well. Okay. All right. So, according to the rules, I'll be making a polynomial that has something plus something x plus something x squared plus something x cubed plus something to the power of 4. And it won't be x, it'll be x minus 1 because the center is 1. So it'll be something like not 2, they're all 1. You don't have to write this thing with the a's like I have, but I'm just, that's a 3. It'll be something like that as long as we choose those letters A correctly. And I can figure them out. And in order to figure them out, I'm going to need to know the derivatives of my original function. So I'm going to do the derivatives. So f of x was, just a second, is x e to the x take 1. F dashed x, I'll have to use the product rule. Okay, so the derivative of x is 1, keep the x minus 1, plus keep the x and do the derivative of that. And then multiply by the derivative of that, which is 1, so that's okay. And so it looks to me like I should do this. That's going to make it a little easier. And f double dashed x, differentiate the 1 plus x, which is still just 1. Okay, that's pretty cool. If I remove the x, take 1, I'll have 1 plus x, which is 2 plus x. Oh, it looks like we're going to be forming a pattern here. I can see it. The third derivative, 1 times e to the x take 1 plus 2 plus x e to the x take 1 times the derivative of that, which is 1, which is 3 plus x. That's looking pretty good. And I reckon I can predict that this one should be 4 plus x. But I'll just do it just to be sure. The derivative of that is 0 plus 1. Okay. Beautiful. Okay. That's great. And then we actually need to know the derivatives at the center. So we'll have to substitute in, sub for short, sub in x equals 1. And so that's going to give us f dashed 1 is 1 e to the 1 minus 1, so, and e to the 0 is 1, and f double dashed 1 is 1 plus 1, which is 2 times 1, which is 2. F triple dashed 1 is 1 plus 1, 2 plus 1, which is 3, and, poo. Sorry, I'm doing it. This is the original function. That's the first derivative. That's the second derivative. The third derivative is 3 plus 1. And the fourth derivative Okay, doing well. And so now we know what the coefficients are, because we'll divide each of these by their matching factorial. The coefficients, this is short for coefficients. The 0th coefficient is just going to be f of 1, which is 1. The first coefficient is going to be f dashed of 1 over 1 factorial, which is 2 over 1, which is 2. The second one's going to be, which is 3 over 2, and a 3 is the third derivative divided by 3 factorial, which is 4 over 6, because 3 factorial is 6, which is 2/3. And the fourth derivative, sorry, the fourth coefficient will use the fourth derivative, which is 5 over 24, and that's not going to give you any simpler. So those are my coefficients. I'm being very deliberate here. I'd probably do this quicker if I was in an exam, but I don't know what your lecturer is going to ask you in your exam, so I have no idea. And so therefore the fourth Taylor polynomial is going to be 1 plus 2x take 1 plus 3 halves of x take 1 squared plus 2/3 of x take 1 cubed plus 5/24 of x take 1 to the 4. And that's how you make a Taylor polynomial. Okay. You can imagine that this takes a while, but if you've got a very friendly function like this one, once you've figured out what the pattern is for the derivatives, you probably don't need to calculate them all separately. But I just want to check something on my screen, if that's okay. So this is the function. I'm just going to zoom in a bit. And this is the point where x is equal to 1, just there. I'm just going to pop that in. That green point just there is the point where x is equal to 1. And I'm going to start making my Taylor polynomial. So that's when I've just got the 1 at the beginning. And now I'll put the next term in. And I can see that it's the tangent at this point. And now I'll put the next term in. And it's pretty good here. It gets very bad here. And now I'll put the next term in, which was 2/3 cubed. And now it's actually looking extremely good over this side. It's a little bit better here than it was. And now I'll put the next one in. And now it's getting better and better as I get close to the origin. And actually it's really good over here, isn't it? Over this side. It's pretty bad when I get to the negative numbers. But this is getting a little further each time, how close it is. And so the more I get, the closer it will get. And already, even at this level, I can't tell the difference between those two functions. It's really good. So the next natural question to ask is, how close is it? Like if I zoom in just here, so that's 0.15. So the distance here is a little bit less than 0.01. And that is the remainder, the distance between these two functions. So I would like you to imagine that you lived in a land where you didn't have a machine that could tell you how far apart these were. And you lived in a land where it was really difficult to calculate those derivatives, and where you were wondering, well, just how many powers should I go to in order to get the closeness that I want? Like I can tell back here, at this stage, we've got about 0.05 at x equals 0. That's how far apart they are. How many terms do I have to put in before it gets to the spot I want? Like, what if I want it to look like it's on top of it? I want it to be so close that I can't tell based on my screen. I'd want this distance to be 1 pixel wide. And so how many powers do I need to put in to get to that stage? And that's a really difficult question to answer. And so what Taylor did in his theorem is to come up with a way of figuring out what that remainder is without actually calculating the Taylor polynomial first. So we can calculate this. We can do a subtraction and go, well, f of 0 minus p4 of 0, and we can figure out exactly what it is. But what Taylor did is find a way of approximating that difference without actually calculating the Taylor polynomial first, which is really cool because that means you can try and guess what power you want. So that's the idea of remainders. So I'm going to go back and we're going to do a remainder for this one. How are we feeling at the moment about what I'm doing? Okay. I'm hoping that this might be useful for next semester, next year's students when they first learn this, so it's earlier. Okay, so the idea of the remainder is to figure out how far apart these things are. And so what we're going to do is we're going to say, well, we know that f of x isn't actually equal to Pn of x. We know it's not actually equal. I can't write equals here, they're not the same. But it will be Pn of x and a bit. That's the idea. So this bit here is how far apart fx and Pnx are. That's an and symbol, by the way. Okay. So let's just let me think about this. So if f of x is above Pn of x, we'll have to go up a bit, and so this will be positive. But if f of x is a little bit below Pn of x, we'll have to go down a bit, so this would be negative. So if this is positive, f of x is bigger than the estimate, and if this is negative, f of x is smaller than the estimate. Okay? And that is a function, we've written it as a function because it will be different for different x's. Just like on my picture, it's further apart in some places than it is in others. So it's different for different x's. Okay, so what we would like is a way of telling how big is this going to be without actually calculating all of these. That's what we want. And what Taylor's theorem does is it tells us how to do that approximately. This is the remainder here. So Taylor's theorem says if Pnx is the nth Taylor polynomial for f of x at x equals a, then the remainder will be this. I'm going to put something here in a second. Okay. I'm going to leave that blank. I'm going to put something there in a sec. So if we were calculating the next Taylor polynomial after the one we've already got, if we did Pnx, we'd go all the way up to Fn at the nth derivative divided by n factorial times x minus a to the n plus n, just n, it's not n plus 1. And we could, if we figured out what the next term in the Taylor polynomial was, it would be this, but it would have an a in this spot. But we know that our function isn't actually equal to a polynomial at all. And so the remainder is totally not going to be this if this is a. But what Taylor did is he said, well, maybe if I pick a different number, it will work out to be the right answer. And that's what he proved. That I can figure out what the next term would be, and I know that's not going to be the proper remainder, but if I use instead of a different number, it can work out to be the correct answer after all. For some z between x and a, depending on which x it is. So that's what he says. He says that if I calculate that and I try it for various different values of z between x and a, one of them will come out to the correct answer. So I wouldn't mind actually trying that on my screen if that's okay. And try and find what this remainder is using Taylor's theorem. So Taylor's theorem says that the remainder for the fourth Taylor polynomial should be, can I do the nth, the fourth? 1, 2, 3, 4, 5. The fifth derivative at some point z divided by 5 factorial times x minus 1 to the 5. It won't be x, it will be 0, because we're doing it at 0, right? We're trying to figure out what it is when we put x equals 0 into this spot. Okay. That's apparently the remainder. And if I try different values of z, then I'll get these different answers for what the remainder could be. But my z has to be between the number I'm thinking of, and the centre. So these are all these different values of what the r could be, and one of them is right. So I'm just going to get it to draw this. Just a second. Just a second. Oh, I know what I'm trying to do. Just a moment. It's going to take me a while to figure out what I'm doing here. Right. Okay. So what I'm doing is I'm drawing the point on the y-axis here that is this plus r, because P4 of 0 plus R4 of 0 should be the correct answer, right? And so if I try these different options for what z is, one of them is correct. It could be that more than one of them is correct, but today this one is correct when z is 0.85. So somewhere in the middle, where if I choose these different values of z, one of them is the right answer. Taylor's theorem doesn't tell me which one it is, but it tells me that one of them is. Okay. So if I didn't know where the real... Just a second, let me go back to that. If I had no idea where the real function actually was, because imagine I'm in 1700 and I haven't got a machine or a calculator to do this stuff for me, I know x e to the x minus 1. I can theoretically calculate its derivatives, but I can't calculate exactly what some of these things are. I mean, I can because I know that e to the 0 is 0, but whatever. If I was trying to figure out what the actual answer was, this is telling me that it's somewhere between here and here. If I choose all the values of z that the theorem says, the correct spot for the function is somewhere between there and there. I don't know where it is really, but it's somewhere between there and there. That's what it says. I choose all the different values of z, and this tells me what the real function actually is. I add the Taylor polynomial answer, and I add on the remainder, and these are all the options for what the answer could be. That's where the real function is, and one of them is right, but I don't know which one. So it can't be any lower. It can't be any lower than this, and it can't be any higher than this. And so I've got this little zone where the real function is, and that's what I would like to know. I would like to know how big should I go in terms of derivatives before that little zone is really tiny, so that I know the function within like one decimal place. That's the idea. Because when I do the fourth derivative, it's if I did the next derivative over a, oh, that's distressing. It's not R4 anymore, it's R5. I think it's struggling to do derivatives. Oh, and we need P5, don't we? Ah, which I don't know. Sorry. I guess this would be 1, 2, 3, 4, 5 of 1. All right, there we go. This is P5 now. So now the real function is between here and here, and that's much more precise. Right, that's good. So we've actually got it to within like about one decimal place now. So that's really cool. I've never done this before on the Desmos. I'm really excited. I didn't even know I was going to do this, so it's very exciting to me being able to draw these pictures and try these things out. Okay. So I should do some examples of using the remainder actually in action. So let's say we're going to keep using the same f of x. So if Pnx which one did I do? 4. If P4x is the Taylor polynomial of degree 4 for f of x is x e to the x take 1. What is, oh no, just a second. At x equals 1, what is the remainder r for 0? Let's find that out. What's the remainder at 0? That's what we've been doing on the screen. Well, what is, we actually don't want to know what it is. I mean, if we actually ask what is the actual remainder, you just subtract them and see what you get. But we want to say, what is, now check with me if your lecturer uses this terminology. Do they use what's an upper bound for the size of the remainder? Something like that? So he might also say something like, in other words, you could say, find the accuracy when P for X is used to approximate f of x equals x e to the x minus 1 at x. F of 0 for f of x. Something like that. Right, what's the accuracy is another way of asking what's the remainder. Like what's the upper bound for the remainder. So when he says upper bound, a bound means something that constrains it, keeps it in place, and an upper bound means, well, it's the biggest answer that that could possibly be. Now, we don't actually need to use a Taylor series to find what f of 0 is, because it's obvious what it is. But I was just pointing something out. Maybe I should do 2. Let's do 2. Yeah, let's do 2. Okay. Okay. So let's actually do that. So the remainder, we know that the remainder number 4 at 2 is f fifth derivative at some point z, 5 factorial x. I'm just going to I'll do it with an x. So that's normally an x here and an x here, and this is the centre there. And so we're using 2 in that spot. Okay. And this is a z, which is why I put a cross through the middle of my z so that you can tell it's not a 2. For some z between 2 and 1. Okay. Well, this is going to require me to figure out a formula for what the fifth derivative is. So I'll find f fifth x. Now f to the 4 was back here. That's f to the, that was the fourth derivative here. And so that should be, differentiate the 4 plus x. Just a second. Give me a moment. The fourth derivative was this. And so the fifth derivative should be derivative of that, e to the x take 1, plus keep that. Derivative of this, which is 5 plus x, e to the x take 1. Okay, which we knew anyway because we figured out the pattern. And so f5 of z, even better. So the remainder is f5 of z over 5 factorial 2 minus 1 to the 5, which is 5 plus z e to the z take 1, 1 to the 5 over 5 factorial. I guess 5 factorial is 120, isn't it? Okay. Fabulous. So here's the question. What could the size of this b? It looks like it's positive, so the absolute value is the same. And we do know that the z is somewhere between 1 and 2. So what you normally do is have a think about what happens when you choose different values of z here and see whether it tends to get bigger when z is bigger or whether it tends to get smaller when z is bigger. So when I look at this function, this is larger when z is larger. This is an increasing function, right? Because e to the something is an increasing function, and 5 plus z is increasing, and when you multiply them, they're still increasing, so i.e. 5 plus z e to the z minus 1 is increasing. And so the biggest this could possibly be would happen when z was the biggest it could be. And so therefore, the largest value is when z is equal to 2. And so the remainder number 4 of z is less than or equal to that, which is 7, got e to the 1, which is e. Now this is an issue, because let's imagine that we really did want to know what the remainder without having to calculate the original function. If we don't know how to calculate x e to the x minus 1, we don't know how to calculate what e is either. And so we really can't use e. We're going to have to approximate e as well. But as long as we know what e is, I mean we do, it's about 2.7. As long as we pick something that's definitely more than e, we can still say a less than or equal to. So I'm just going to pick 3. Like this is totally less than 7 times 3 over 120, since e is less than 3. And this is what they would have done back in the day. And we're trying to imagine a world where we have to make up the maths ourselves. And 21 over 120, well, I'm allowed to use a calculator for that. But, you know, 20 divided by 120 would be a sixth. And a sixth is about 0.17. But I'm just going to ask my computer what that is. Aha, look, 3 goes into 120. That's cool. So that's 7 over 40, which is half 7 would be 3.5, and you divide that by 2 again, which would be 1.75. Beautiful. That's pleasant, isn't it? I love it. Okay. I mean, that's what calculators are for. But, I mean, if we're allowed to use a calculator that has e on it, then we could have just subbed that in. That would have been okay as well. But what we're imagining is that the only calculator we have that does plus minus times divide. Okay, so we have that. It's not z, sorry, that's not supposed to be a z, that's a 2. Is less than 0.175. So that's pretty cool. We've got it to within, well, it's definitely good to the nearest whole number. Okay. So the other question we could ask is, what does n have to be to do that to be absolutely sure that we can get within a certain accuracy? Now, my computer actually says that this accuracy is way, way better than this. But we are just using Taylor's theorem, and so this is the best that we can do. I'm just going to go back and have a look at the picture. And let me turn the... Oh, that's P5. Damn it. So here we are at 2. Right, the distance between these, let's get a good one. So this is 0.1, 2, 3. Oh yeah, 0.01, 02, 03, 04, 04, 0.05. So that's about a quarter of what we've actually calculated. But that's not too bad, actually. It's a pretty good estimate. So our question is, well, how accurate do we need it to be within, say, 2 decimal places? How many terms should we calculate? Should we use P4? Obviously not P4, that's not good enough. But what about P5 or P6 or P7? How far should we go to get 2 decimal places of accuracy? So here's another question. What should n be so that Pn2, as you know, Taylor of degree n at x equals 1 is accurate, damn it, at x equals 1 for f of x. Not good at judging space today, and I'm not even writing on the screen. What should n be so that Pn2 at Taylor polynomial of degree n at x equals 1 for f of x equals x e to the x minus 1 is accurate to 2 decimal places? So that's my question that I'm going to ask. So, okay, well, we know that 4 isn't good enough, so it's going to have to be more than that. But what we want to know is, well, how far do we have to go? And in order to do that, I'm going to need to know what a formula for the remainder in terms of n. So I need in terms of n in order to do that. So I'm going to have to figure out that pattern. We already had from the earlier pattern, we saw that f dashed was 1 plus x, and f double dashed was 2 plus x, and f triple dashed was 3 plus x. So we're pretty sure that fnx is n plus x. Now, if you were in a particularly rigorous mathematically rigorous mood, you would have to use mathematical induction to prove that. We decide not to, because it's not the flavour of the day when we're doing Taylor series normally. We're normally allowed to just look at it and go, oh, well, that's the pattern. Okay. And so that means that remainder n for 2 is fn plus 1. Oh, we need a formula for that, won't we? Just a second. We actually need n plus 1. Right. So remainder n for 2 is fn plus 1 of z over n plus 1 factorial times x, well, 2 minus 1 to the n plus 1. And this bit is n plus 1 plus z e to the z take 1. And that's 1 n plus 1, and I don't have a choice about this one. And looks like that's just going to work out to this. But again, it's only for some z between 1 and 2, right? Between the centre and the number I'm thinking of. And we already noticed that this function is increasing for increasing z. So note this is an increasing function of z. So its maximum on this interval is at 2. And so therefore, this is less than or equal to n plus 1 plus 2 e to the 2 minus 1 factorial which is n plus 3 e over n plus 1 factorial. Okay. I guess we could go that's less than 3 of this, just because we're doing this sort of thing. So here's the thing. We would like this error to be small enough to be sure that we're within 2 decimal places. So if I make this small enough so that we're within 2 decimal places, then that will have to be as well, because it's smaller than that. So all that means is I need to pick a number so that I can be sure I'm accurate to within 2 decimal places. So it's 5 times 10 to the minus 3. And the reason that works is, if you're accurate to 2 decimal places, that means that the difference between the thing you round off to and the thing that you are is in the next decimal place. So when you round off to 2 decimal places, you look at the 3rd decimal place, and the 3rd decimal place is 10 to the minus 3. That's the 3rd decimal place. And you know if the 3rd decimal place was under 5, you would round down. And if the 3rd, yeah. And so that's why the 5. Yeah. But I've done this for so many years that I can see 2 decimal place accuracy and immediately write down 5 times 10 to the minus 3. And if it was 7 decimal place accuracy, it would be 5 times 10 to the minus 8. And if it was 12 decimal place accuracy, it would be 5 times 10 to the minus 13. Yeah. So if you want to round off to 2 decimal places, you have to look in the 3rd decimal place in order to decide. Okay, so we will choose n so that this is less than 5 times 10 to the minus 3. Well, I'll probably just start trying them and see what happens, really. Usually it's a trial and error sort of thing. I know that it didn't work at 4, so I'd go to the next one at least. And I'm thinking that I need n plus 1 factorial to be more than, quite a bit more than 3 times n plus 3. So I'm thinking that 5 factorial is 120, and Oh, that one was going to work, was it? 6 factorial is 720. I'm just going to try it. So 3 times 9 divided by 7 factorial. Oh, we are so close. When I asked my calculator, it came out to 0.0053. We are just a little bit too big. And so we're going to have to go to the next one. So it looks like if we want to get 2 decimal place accuracy, we actually end up with 3 decimal place accuracy, which is pretty cool. So need n to be greater than or equal to 8. So these things are usually trial and error because they usually have a factorial in them and you're just going to have to try. Actually gives 3 decimal place accuracy, but you know, that's good enough. We couldn't get exactly 2 decimal places of accuracy. This actually doesn't actually work very well because rounding off is a bit weird. 2 numbers that round off to the same thing to within 2 decimal places can actually be quite far apart from each other. Yeah. And 2 numbers that round off to different things to 2 decimal places can actually be really close to each other. But we're not going to worry about that. Okay. I think that's everything I could say about remainders off the top of my head. It's now time to ask you if there's anything that I've missed or any particular problems or what ifs. If you look at what I've done and you say, well, David, what if it was this instead? How would I deal with that? Those are good sorts of questions too. So if you've got any of those, let me know. Where are you? Oh, here. It's because for 2 decimal place accuracy, if I was rounding off to 2 decimal places, I would look in the 3rd decimal place. So this is what's in my head here. So here we are. If I was rounding off just a random number, right? If I was rounding that off to 2 decimal places, then I would look here in the 3rd decimal place. And the 3rd decimal place, this is 10 to the minus 1. This is in the position 10 to the minus 2. This is in the position 10 to the minus 3. And so that's why the 10 to the minus 3. The 5 is because you know that if you go further than 5 away, then you'll round off to the next thing. And that's why. Took me years to understand that, like literally. I mean, I think I remembered it when I did maths, when I learned Taylor series, and I could just remember it in the exam. I repeated it to myself, but I never understood it until several years later. So, yeah. Okay. Right. So the other thing that you mentioned was ratio test. So I might mention that too, because it's in the same sort of zone. So this is Taylor series, but at the moment I haven't even talked about Taylor series. I've just been talking about Taylor polynomials. We've been stopping at a specific n. We've said, look, if we stop at n equals 8, we'll have the right accuracy that we want, and that'll be great. So I guess we've got that, you know, can use P8 of 2 to e to the 2 minus 1, right? That's what we can do. F of 2 to 2 decimal places. Okay, so that's what we've been doing, but we can go all theoretical on it, mathematics, and say, well, if we did this process forever and did x to the 10 and up to x to the 1,000 and x to the million and just did it forever, we could be actually equal to my function. Now that seems silly in some ways, but mathematicians love infinity, because even if we write 1/3 as 0.333333, it's never equal to 1/3 if you stop. No matter how many 3's you have, you could write 100 3's, and if you stop, it's still not exactly equal to 1/3. You have to go forever. And that's the same idea as these Taylor polynomials. So, Taylor series. And also, it turns out that if we think about the ones that go forever, we can shortcut the process, and if we know what the answer is for some, we can figure out the answers for others without having to calculate the derivatives. Because a Taylor polynomial is always the beginning of a Taylor series. And if I can figure out the entire Taylor series, I can guess the Taylor polynomial from that. So that's another way of doing it. So let's do Taylor series. So if, instead of stopping and figuring out how accurate it is, you went forever, you could actually say that it's not just equal to the Taylor polynomial and an error, it's literally equal to the infinite Taylor polynomial. Forever. So now we're going to say, instead of stopping, we're going to go forever, and it turns out it's the same coefficients that you would do from a Taylor polynomial, and it works out quite well. And it also turns out, not only, so when we did the Taylor polynomial, the best choice in terms of nearness to my function, at least nearby to the point I was interested in, sorry, I should do it with an x minus 1, but it doesn't matter, or x minus a. The best choice was to use the derivatives. If you want it to be equal to an infinite polynomial, there is only one choice. It's not like there's a best choice. There's actually only one, and nothing else works. And the only choice you can make is that an is the nth derivative of x at the in this case 0. I'm going to put it in, I'm sorry. Is for the coefficient to be this. It's the only choice is for that. And that's fabulous. And it's really useful to know that there's only one choice. Because what that means is that if you happen to find one that works, then it also tells you the derivative of your function. So what we normally write, there's not an n there, sorry. We normally write it as an infinite sum like this. And in order to do that, we have to define 0 factorial to be 1, but that's okay. Because we didn't really know what 0 factorial meant before. It doesn't really mean anything. We just decide that 0 factorial is going to be 1, and then this formula works. Okay. So that's great. It's lovely. And if you want to find one of these, you're going to have to find a pattern in the derivatives if you want to actually find one of your own. So, for example, we found before that for f of x equals x e to the x take 1, the nth derivative was n plus 1 e to the x take 1. No, n plus x, wasn't it? That's what we found earlier. So f of n plus 1, sorry, not 1, n plus 1, damn it. Fn of 1 is 1 n plus 1 e to the 1 minus 1, which is n plus 1, just n plus 1. And so f of x is actually n equals 0 to infinity n plus 1 over n factorial x take 1 to the n. So if you happen to be able to find a formula, a pattern for your derivatives, then you can create a Taylor series from scratch. But those who have trodden this path before us have done all the work and figured out the Taylor series at x equals 0 for a lot of familiar functions. Just a second. Okay. I mentioned something earlier that I didn't say. If your centre is 0, it's called a Maclaurin series, because Maclaurin did it first before Taylor. Actually, I think they did it at the same time. I'm pretty sure the reason they both get named is because they did it at the same time. Maclaurin did it just for 0 and Taylor did it for everything. And so they wanted to give Maclaurin credit. And so, yeah, Maclaurin was Scottish and Taylor was British. And I think more Scottish people need some credit over and above the English people, I reckon. To be fair, a lot of this stuff was done in India before they did it in England, but we don't get to talk about those people, sadly. And that's true of a lot of mathematics, and we end up with British people naming them even though it was invented earlier by somebody else, which is our shame, really. Okay. So just as a note, Taylor with centre x equals 0 is called Maclaurin. Okay, and so there's some famous Maclaurin series. So the most famous of all Maclaurin series is this one. That one. So if you go e to the x, then the coefficients are 1 over n factorial. Yeah, that's the most famous. And there's another one that's pretty famous, but you don't normally call it a Maclaurin series. It's this. And this thing here is called a geometric series. So the interesting thing about this is that this one up here works no matter what x is. Like you might have to go a very long way before it's the correct answer, before it's close to the correct answer, but it always works if you go forever. This one will only work if x is less than 1. And that's where we get to this thing about convergence in a second. And the other two famous ones are sin x and cos x. And I'll just write them down in the order I remember it. So sine x only has odd powers of x, and like odd exponents, and cos x only has even exponents. And so for it to be odd, I need a 2n plus 1. Because if you multiply something by 2 and add 1, you always get an odd number. And for it to be even, and I'm going to have to divide by that. So I'm pulling a little trick here, actually, because normally the number you use here is the same as the number you use here. But what I'm actually doing is I'm saying I can keep track of which odd number I'm up to by keeping track of the n in this formula instead. And then I'm going to put a minus here, like that. So that's the order I write it in. The cos x is the even ones. Well, it's that. I will not be offended if people have to, go to the toilet or anything. So they're the most famous ones. There are others. Oh no, there's one more. Just a second. I don't want to use n. Your lecturer probably used k. Yes, they did. Look at that. Okay. Yeah, okay. With this symbol, when we did combinatorics, this is in the notes, so I don't know if he talked about it or not. Did he? Yeah. Anyway, this one's famous. It's called the binomial series. And this thing, most people read that aloud as k choose n. Because if k was a whole number, that would be the same as the number of ways to choose k objects out of n objects. And so it doesn't really make sense if k isn't a whole number. Like if you had a half choose 3, that is completely nonsensical, right? Because how do you choose 3 things out of half a thing? But we're mathematicians. We're just going to take the formula that we would normally use for k choose n when k is a whole number and apply it to when k is not a whole number. And so just so you know, like 15 choose 3, for example, would have 3 times 2 times 1 on the bottom for this, and it would have 15 times 14 times 13 on the top. And see how there are 3 terms here? There's 3 terms here. And these ones go down, and these ones go down. So you always have the bottom number, that number, all the way down to 1. And then on the top, you go down the same number of steps as there is on the bottom. So that's what 15 choose 3 is. And if you had like a half choose 3, which doesn't make any sense, right, in a story, there's no stories where you have half a thing and you can choose 3 of them. But mathematically, I can do the same formula. I can go 3 times 2 times 1 and have a half, and then go down by 1 to minus a half, and then go down by 1 to minus 3 on 2. And that's the answer. Pretty silly, but it works. So I don't know how much your lecturer wants you to do this, because Taylor series was pretty early, wasn't it? Taylor series was the point at which your lecturer went, ooh, I need to think carefully about how I pitch things in this course, based on people's experience. So anyway, these are the famous Maclaurin series. And so they're the ones that you don't, unless you're specifically asked to prove it, they're the ones that you can just use. Right. And essentially what this tells you is what the derivative of this is when x is 0. Yeah, divided by the factorial. And if you think about that for a little bit, you can find a way of remembering this, because look at this. The term of the Maclaurin series should be the function's derivative divided by n factorial. And the derivative of this, you'd multiply by k, and the k would go down by 1. And then you'd multiply by k minus 1, and then the k would go down by 1 again, and you'd multiply k minus 2. That's what this is saying. It's just holding that information all together in a single symbol. Yeah. Right. So let me just do something. If you know what the Taylor series is, then you can write down, without doing any of the derivatives, what the Taylor polynomial is. So just as an example, f of x is 2 times 1 plus x. Something like that. No, I won't do a 2. I'll just... If f of x was that, then you could say, write down p3x, the third Maclaurin polynomial. For f of x. Because I know what the Taylor series is, I can just write it down. So f of x is root 1 plus x, which is 1 plus x to the power of a half. And so therefore, p3 of x will be 1, because that's what the thing says. You always start at 1. And then you do a half, choose 1x, plus a half, choose 2x squared, plus a half, choose 3x cubed. That's the idea of this formula. I can go straight to finding out what the Taylor polynomial is based on the Taylor series. And so p3x. So a half choose 1 would have a 1 on the bottom and a half on the top. And a half choose 2 would have a 2 times 1 on the bottom and a half times what I get when I go down by 1 on the top. And a half choose 3 would have 3 times 2 times 1, a half minus a half minus 1.5, like that. So all this works out to be an eighth. And that 3 cancels with that 3, and I get plus a 16th. 1, 2, 3, 4, yeah. And this is a pretty good approximation for the square root of 1 plus x if x is close to 0. I have no way of figuring out what the remainder is from this information. The only way to figure out the remainder is to actually calculate the derivatives, sadly. Because the Taylor polynomial has the centre subbed in, and so you don't actually know what the formula for the derivative is, and you can only do the remainder if you have a formula for that, because you have to put z into it. So I can't find the remainder this way, but I can find what the polynomial is. And I can be pretty sure that it will be pretty good when x is less than 1, because my remainder theorem has x minus 0 to the n. So if x is less than 1, that'll be a small number to the power of n, and a small number to the power of n is even smaller. So you can be pretty sure that's pretty accurate when x is less than 1 based on the remainder theorem. Okay, so that was just a way of saying that you can find out what it should be if you know the Taylor series. So I just want to do one more thing, which I think is fun. I don't know if your lecturer wants you to do this, but I think it's fun. So this is the one that we had before, for e to the x minus 1. No, the Maclaurin, sorry. No, that's all right. Find the Taylor polynomial for f of x equals x e to the x minus 1 at x equals 1 from the Maclaurin series for e to the x. That's what I'm going to do. Ready? It's so much fun. Okay. So I know what the Maclaurin series for e to the x is. It's this. All right? And the Taylor polynomial for x e to the x minus 1 at x equals 1 will have x minus 1s to the power of something in it. So I need to create something like this that's got x minus 1 to the power of something. So I could do that by subbing in x minus 1. Yeah? Okay. So this is now a Taylor series for e to the power of x minus 1. Sweet. Okay. And it has to be, because if you find an infinite series with x to the minus 1 to the n, it is, and it has to be the Taylor series, because there's only one. Okay. So now I want to multiply this by x, right? Oh, that's a bit sad, actually. That's a problem. Because I've broken the thing of it being having x minus 1 to the power of something. Ah, damn it. I'm going to have to put an x minus 1 in. Well, I can do that. X is the same as x minus 1 plus 1. It's probably quicker for us to do this with the derivatives, but I just wanted to show you what was going on. So the x minus 1 times this will be x minus 1 to the n plus 1. And the 1 times this is that. Doing well. So I can divide them separately by n factorial. Okay. Right. I've got different n's. I guess I could do the sums separately. Well, I don't know if this is helpful to you, but I'm hoping that you're seeing all sorts of fun ways to manipulate infinite sums. It may have been a bad choice, because it's not being nearly as simple as I would have liked. Well, I guess this one really starts at 1 up here. Okay. So what I did there is I went, when I start at 0, this is 1, and when this is 1, that's 2. So if I said that I started at that this is 1, then this has to be 1 less than that. So one way of thinking about this is to subtract 1 from both of these and add 1 to all of these. So these went down 1 and these went up 1, and then it all works out to the same answer anyway. And so what that means is, except for the n equals 0, these match up neatly And so I've got wow, possibly safe to ignore this one, because I'm sure your lecturer would not give you this one. So this bit here, I've separated into the bit with n equals 0 and all the rest of them. And now these both start at the same spot, and they both have an x to the power of n, so I can actually add them together now. So that's 1. And these both have an x to the n in them. And technically n factorial, oh yeah, that's so cool. I'm so excited, but I can't stand anymore. Watch this. N factorial is the same as n lots of n minus 1 factorial. Because to get to n factorial, first you have to get to n minus 1, and then you times by an extra n. We are so close. Are you ready? Ready? Yeah, it's so good. I'm so excited. Because we know what the answer is. This is n over n. And so we get n plus 1 over n. So sorry, it's a minus 1. N minus 1 factorial times n is n factorial, and we've multiplied by n plus 1. And that's exactly the formula we had before. That's so cool. So cool. Wow. Yeah, that was way more work than us actually calculating the derivatives, I'm sorry. It was supposed to be magically faster, but it just wasn't. I did use a few cool tricks along the way, which are fun things to know. Things like n factorial is the same as n minus 1 factorial. And things like if it's got an n plus 1 in it, you can make the power go down by 1 by adding 1 to each of these instead. That's a neat little trick. If you ever see it again, I don't know how many maths courses are in your degree and whether you get to do another one, or whether that trick happened at any point or not. So they're just some useful, I'm hoping that along the way we've got some cool little strategies for dealing with sums. Yeah. But this is the exact formula we got before, the n plus 1 over n factorial, which is kind of cool. I'm pretty happy that that actually worked out. So here's the question. What if you do convergence? Okay, so here's the question. Some of these only work for some x's. So this one here, this only worked when x was less than 1. And actually, this one here also only works when x is less than 1. I mean, it'll work perfectly well for all x if x is if k is a whole number, but otherwise it only works if x is less than 1. So, and some of them always work, and it would be useful to be able to tell from just a random infinite series which x's made it converge or not. That would be useful. So give me a second. Where's the bit with the infinite series? Did your lecturer do a thing with radius of convergence? Yeah, there it is. Found it. So here's a question. How did we decide that, for the absolute value of x is less than 1? If you have to go, that's fine. How did we decide that? And this is called an interval of convergence. Like this thing here is called a radius of convergence. So how did we decide? And we decided by doing the ratio test. So the bit in the notes is pretty, there's not all that much on it. So the easiest way is to just do an example. No, we want the interval of sorry. That's the radius of convergence, and this entire thing describes an interval of convergence. Because this describes a little piece of the number line of x's we're allowed to use. Okay. All right, let me just make one up. Yep.
So the graph that we did before, like where we plotted the graphs and
This thing.
so when we plotted the graph, we brought up the series where we got approximately to a particular point. Where is this particular point that we use the convergence of the
All right. So this function, the interval of convergence is the entire real line. But some functions, it's not. So why don't I draw a different function, hey? That is an excellent question, by the way. Okay, so that's what 1 over 1 minus x looks like. Okay. Which you may notice has a horrifying issue at the point where x is equal to 1. Okay? So let's actually write down the Taylor polynomial for this, and I'll show you what the problem is. So this is a geometric series. It's one, it's the sum. Okay, and I'm sorry, 0. So when n equals 1, when this top number here, this capital N at the top, is 1, this is what this. Let's change the colour. This blue line is the Taylor polynomial. So you'll notice that this function is really no good whatsoever over here. And in fact, this line just gets further and further away from this line as n increases. And so it doesn't converge. This line just gets higher and higher and higher. So over there it doesn't work. And it does get closer and closer to the function here. Sorry, here. It's closer and closer to the function here, and it gets closer and closer to the function here. But you'll notice that it just flips back and forth and gets horrible here. So, okay. It's not flipping back and forth because it's not doing every number. But so this actual formula here doesn't converge to something when the x is outside this zone from -1 to 1. It gets better and better. You can see if we zoom in just here that the place that it's working for is getting a little further and further along, right? But if you go beyond this mark here, it just never works ever. Does that answer your question? Yeah. Whoa, whoa, ah. Oh, it's thinking very hard because I've made it calculate 50 powers of x. Okay. I'll have to stop soon, but I really want to finish this example. Yep, that's the one I'm going to do. So I'm just going to read it aloud. I have the sum from n equals 1 to infinity of 2 to the power of n plus 1 times x plus 1 to the power of n over 3n plus 4. Okay. So it's not too far from being a power series. If this 3n plus 4 wasn't there, and if that was just a 2 to the power of n, then I could write it as thing to the power of n, and it would be a geometric series. And so I could borrow what I know about geometric series to do it. But this one is not, so I need to do the trick. And so to do the ratio test, it's called, what you need to do is look at this whole thing and call it an. This is how I do it. I don't know how your lecturer does it. Oh, yeah. Your lecturer just calls this bit that's next to the x an, but I just call the whole thing an. And you go an plus 1 divided by an. Yep. So you take the next term divided by the previous term. So in the ratio test, first we have to calculate this. So I put n plus 1 in here. N plus 1 is 2. N plus 1, 3, n plus 1, like that. And an is this. That thing. Technically, we need the absolute value of this, but we'll get to that in a minute. And this we have to do some algebra on to make it as simple as we possibly can before we do anything else. So dividing by a fraction is the same as multiplying by the reciprocal of the fraction. I put it up the other way, and so that's okay. And now all of this I can just combine together into one big fraction if I like. This part that I'm writing here is not strictly necessary, but it's just going to be easier to see what's going on. what we want. So you multiply the top and you multiply the bottom, and so that's what I've done. And I've just arranged them so that the pieces that look similar are on top of each other. So here we go. This divided by this is 2, because we subtract the powers. N plus 2 minus n plus 1 is 2. So we get 2 to the 1 there for this bit here. This bit, not quite so obvious what's going on there, so I'll just leave that there. And this divided by this is this. Because n plus 1 divided by n, a thing to the power of n plus 1 divided by a thing to the power of n, you subtract the powers and we just get 1. Okay. And that should usually happen when you do this. So I need the absolute value of this, and I need the absolute value of this, and I need to do the limit of it as n goes to infinity. So when you do absolute values and there's things multiplied, you can do the absolute value of each bit separately when it's multiplication. The absolute value of 2 is 2. All of these are positive numbers, so the absolute value is the same. And the absolute value of x plus 1 is the absolute value of x plus 1. Because if x is like minus 3, this will be a negative number, so I'm going to have to do absolute value. So now I need to do the limit of this as n goes to infinity. Okay, so when I do the limit of this bit doesn't involve an n, so that can come out of my limit. And this bit doesn't involve an n, so that can come out of my limit as well. But just, I'm going to write that explicitly. I probably should have expanded out this 3n plus 1, a page ago, but I'm stuck now. I should have expanded that out ages ago. So now I need to find the limit of this. Did we do limits in this course? I hope so, because otherwise we couldn't do it. Or have we done it before? Okay. My usual way of doing limits when the n goes to infinity is to divide the top and the bottom by n, or the biggest power of NIC. I can also see that if n is an extremely large number, like 1,000,000, these two are almost the same. Because like 1,000,000 and 1,000,001 are not that different from each other. So what I would normally do is divide everything by n. And now when n goes to infinity, I get, well, the 3 stays. 4 divided by infinity is 0. 1 divided by infinity is 0. 4 divided by infinity is 0. And so I get that, which is 3 divided by 3, which is 1. So I have almost finished the ratio test. The ratio test says that if this is less than 1, then it converges. So the ratio test, if the answer I just got I'm running out of time, only a couple of minutes to go. And so that's less than a half. And now we've found the radius. The radius is a half. So once you've gotten it as absolute value of x plus or minus something, this bit is a half. But we also have that that means that this thing must be between plus and minus a half, because that's what happens when you have an absolute value is less than a number. And now if I subtract 1 from everything, it'll only work if x is between minus 1.5, minus 3 halves, and minus a half. So to get from this line to this line, I subtracted 1. So that's my interval of convergence. I actually don't know if it converges at the... I have to check what happens when x is each of those numbers, technically. 3 minutes, all right. So if x is equal to this bottom number, then that means that the x plus 1 is minus a half. And so we get, where's the original sum? 2 to the n plus 1 minus a half to the n over 3n plus 4. Oh man. Well, I guess 2 to the n on the bottom would cancel with that, so I'm going to get... And that one will converge because it alternates and the bottom goes to infinity, like that, and it goes to 0. Since it's alternating. And if x is minus a half, then x plus 1 is plus a half, and so oh wow, I've made it more complicated than it needs to be. I'm so sorry. That's what this algebra works out to be. And that one does not converge because it's a harmonic series, they call it. If the top is a number and the bottom is linear, then it won't converge. So that may be more than was necessary. I'm sorry. I don't know what level to pitch it at. And so what we have discovered is that it converges for everything between here and here, and it converges for this number here, but it doesn't converge for this number here. So the interval of convergence is the x such that minus 3 on 2 is less than or equal to x, which is less than minus a half. It could be this, but it's not allowed to be that. That's how I find an interval of convergence. Yeah. So one thing I would like to say is that if at this stage here you end up without any x's, or you just get 0, then if this is 0, then no matter what x is, it's always less than 1. You just get 0 is less than 1. It converges when 0 is less than 1. And that's always true. And so it converges no matter what x is. And the interval of convergence is the entire real line. So just... then converges for x with 0 is less than 1, which is all x. Sorry, it converges for x with 0 is less than 1, which is all x.